Unless you manually are.
Okay, your calculator's out. Today, I want to show you what how we can find the area using multiple ways. I feel like if you understand this process, then everything else, this unit kind of falls into place. We're like the hardest thing is getting the arrangement of your setup, because if you can get the setup correctly in terms of what equations you're using and what bounds you're using, then everything is just calculated, right? So really, we're not doing much calculus here. We're just identifying the function, the equation, identifying the appropriate bounds, and then just plugging in, making the calculator do all the work. So, if we can get that down, then this would feel like an easy unit. The issue is sometimes students have trouble identifying how to set up the equation and how to set up the bounds. But I feel like this is this is the most important thing here. If you can do this, then the volume is all going to fall into place. It's all using the same concepts. We're just extending it into a volume format. So let's see how this goes. We have R and S being regions in the first quadrant shown in the figure. Region R is bounded by the x-axis and the graph y equals 2 minus x cubed and tangent of x. So 2 minus x cubed is the one that has kind of that negative slope about it, and tangent of x is the one that kind of has that positive slope about it. Region S is bounded by the y-axis and the graph of y equals 2 minus x cubed and tangent of x. We're going to find the area of S both ways. Okay, so I'm going to just lightly fade in where S is. So we'll do a top minus bottom relationship, which will feel easier because everything is going to be set up for us. Right minus left is a little bit more challenging because the equations need to be rewritten, the bounds need to be revisited. So region S, if we think about the fact that this is just really top minus bottom, we're adding infinitely thin rectangles from one end all the way to the other end. We know that this left end is easy. That's just x equals 0. But the endpoint here is going to be the boundary of our shader region. Okay? So we're going to make the calculator find that location for us. Okay. Let me zoom in and we can practice plugging this into our calculator. Okay, so in your calculator, go to y equals. We'll type in, oh yeah, make sure, yeah, we should always be in radian mode. So mode radian. Okay, tangent of x, sorry, y equals. Doesn't matter which one you put in first. Tangent of x and 2 minus x cubed. I'd like to start off with zoom 6. It's probably going to be too much or too far. We're probably too zoomed out. Yeah, so we're just looking at that little region there. So you can either go to window and adjust it, or you can go to zoom box and just draw a box around the region that you care to look at. So if I hit enter, at zoom 1, I'm just going to move my cursor to where I want the upper corner of my box to be. So I just moved it to in that second quadrant somewhere. I'm going to hit enter once, and then you're just going to use your directional arrows to draw a box. maybe that's too much. I just really care about that region there. Hit enter again. Once you draw the box, hit enter again. And it should look very similar to what you have on your paper. Okay, any questions? Now, we want to find this intersecting point. So go ahead and do second trace, intersect. So you're just going to pick a point that is close to the intersection. Don't go directly on the intersection. It'll confuse the calculator. So first curve, question mark. So just identify what you want to be your first curve. It doesn't really matter. Hit enter. And the calculator usually will just toggle to the other curve. And it says second curve. We want to get that confirmation. Hit enter again. And it's going to say guess question mark. So now it's going to try to find the closest intersection between these 2 points. I mean, there's only one intersection, so it's only going to find this point. But if there were 2 intersections, then just make sure that you are picking points that's close to the intersection that you want to look for. It's always going to look for the closest intersection. It's not going to find both intersections for you if there were multiple intersections. Hit enter a third time. And let's write down, I know right now we only need the x value, but let's write down both the x and y values since the y value will come in handy a little bit later. Let's round to 3 decimal places. So 0.902 and 1.266. We're not going to really need that 1.266 right now because if we're doing top minus bottom, everything's in terms of x. Okay, so this should be a quick, easy setup because we see, let me just draw one representative rectangle so you can kind of see what's going on here. Ultimately, we have infinitely thin rectangles, but they are stacked this way. They're stacked from the y-axis all the way to where that intersecting point is. So we know that this is a good relationship for top minus bottom because these equations are already in function form. They have that y equals about them, which means that the right side is ready for top minus bottom. And then we have our bounds for our shaded region. So our area is going to be an easy setup from left bound to right bound. So from 0 to 0.902. Top graph minus bottom graph. So I'll use green for top and then red for bottom. Okay, so the graph on top is the green graph. That's the 2 minus x cubed. Minus parentheses. I guess the parentheses is not going to matter for us since there's only one term. But I think it's always a good habit that anything that follows a minus sign, protect it with a set of parentheses in case there are multiple terms. Bottom graph is the one in red. That's the tangent one. And we just plug this in the calculator. Now, I like to make it a habit of, now if you enter all this into your main screen, that's fine. But eventually these functions, especially when we're talking about volume, these will get more and more complex. So the way I like to do it is I like to start getting into a habit of calling my functions from y1 and y2. So I have y2 holding my 2 minus x cubed, and I have y1 holding my tangent of x. So again, the benefit of doing it this way, calling it the functions, is that there's less parentheses you have to worry about later on when we have to square everything and there's a whole bunch of parentheses involved. There's less parentheses involved if we can kind of let y1 and y2 hold these functions. And that way you don't get stuck with, oh, wait, I forgot a parentheses, or I need a closing parentheses here or opening parentheses there. It just looks a little bit cleaner. I think that's what I just want to encourage. But it's not wrong. If you want to put everything in the main screen, that's fine. It's just looks a little messier. All right, so I'm going to do alpha trace. For me, I have y2 holding my 2 minus x cubed. And then my tangent is holding y1. But if your order is different, then just make the adjustment. And if you accidentally got the order wrong, you would know because your answer would be negative. So if you accidentally got the bottom minus top, you would get an instant feedback to tell you that your bounds are not quite right, because you would get a negative 1.16. Okay, so that's pretty straightforward, right? We're making the calculator do all the calculus for us. We just have to worry about the setup and the bounds. This is area, so we're just going to remind ourselves that we're dealing with area, so let's call it unit squared. Okay, any questions with part A or part one? All right, so this is easy, okay? Right minus left is a bit more challenging because now we want to think, what if we wanted to add up rectangles, but we were adding rectangles horizontally? What if we were stacking rectangles from one end to the other, like this way? So then we have to do like right minus left. But the issue is that as we imagine the number of rectangles that we can fit into the space, are these rectangles always going to hit the same graph? Up to a point, right? What's going to happen up here? What's different about this rectangle up here versus a rectangle down here? Do you guys see how the right endpoint of these rectangles are not sitting at the same graph? Right, this bottom one is is involving the tangent. This top one is involving the 2 minus x cubed. So we have to rely on two separate integrals, right? Because one integral won't be able to, we don't have a consistent curve on the right for the entirety of this shaded region. So we have to think of it as two separate equations. Now, anytime you see a horizontal rectangle, that's an indication that your equation needs to be written in a different form. Okay, we have to solve for x. We have to get it into the form of x equals. It's not as easy as just saying, oh, x equals tangent of y. We have to, algebraically actually move things around and solve for a different variable. So let me just show you what that would look like. So if I have tangent of x equals to y, and if I want to get it into a form that is good for right minus left, I have to solve for x. If I have to solve for x, I got to move that tangent over. If I move that tangent over, we don't divide by tangent, right? We use inverse tangent. So x is equal to inverse tangent of y. So now this is going to represent the curve that I have in red. Right? This is what we want to use. If you can get it into x equals, you know that the right side is going to be fit for this right minus left formula. Ultimately, if you had a choice between these two, you'll probably pick this one every time. But I want to show this method to you because sometimes problems forces you into this form. And so, knowing this form is going to be beneficial, especially when we get to volume. Okay? Sometimes with volume formulas, you have no choice but to get it into a right minus left form. Likewise, the y equals 2 minus x cubed is not in the proper equation form. We can't just say, oh, x equals 2 minus y cubed. We actually have to solve for x and rearrange it and get x by itself. So if I have y is equal to 2 minus x cubed, I'm going to move that x cubed over to the left side. And I want to solve for x. I like that x being positive, so I moved it to the left. And then I'm going to take the cube root, to solve for x. So x is the cube root of 2 minus y. So this is my graph in green. Okay, this order pair is going to be helpful again for us. Let me write that order pair. Sorry. This order pair here is again 0.902 and 1.266. So we're going to be stacking two different rectangles, one from 0 up until where the graph is going to change. And then for the upper region, we got to go from this point up until this point here. So this point, it's just the y-intercept of my 2 minus x cubed. So if I want to find y-intercept, I can simply plug 0 in for x and solve for y. So if I plug 0 in for x, my y is simply 2. So my y-intercept there is just 0, 2. Okay, all right, we have everything that we need to set up our integral. Ultimately, we should get the same answer as part A. We're talking about the same region, but we're just doing it in a different way. So let's do the bottom first. So area, go from bottom to top. So we'll look at the bottom region here involving the red curve, involving the tangent. So it's going to be from 0 to 1.266, right? That's the y value where the two graphs will split. And follow the formula here, right minus left. The graph on the right is the red graph, which is, we don't want to call it tangent x, it's inverse tangent of y now. If we want to do right minus left, everything that shows up needs to be in terms of y. And then the left, right, the left boundary of my shaded region is the y-axis. What's the equation for the y-axis? Good, x equals 0. And you know that all these are going to be good fits for a right minus left, because if you want to do right minus left, it's not necessarily going to show you y's on the right, but it'll always show you an x on the left. So if we see x equals, you know that whatever you see on the right side is a good fit for this right minus left relationship. So right minus left, this will give me this bottom region. Okay, plus, let's do the upper region. The upper region is going from this 1.266 all the way up to this y value of 2. And then right minus left. But now the graph on the right of my upper region is the green, and the adapted green equation that I want for right minus left is cube root of 2 minus y. Right minus left. And the left endpoint is again the x-axis, sorry, y-axis, so minus 0 dy. On paper, you're using y's, but in your calculator, you're going to always use what? Always use x, yeah. Don't try to force the calculator to do a different variable. Just always use x in your calculator. I would just enter it in directly, and maybe it's not worth the trouble to put it into y1, y2, since we're not going to be graphing these. And also we can drop the zeros, right? So that should make it a little bit cleaner as well. We can just drop the zeros. Okay, let's try practice plugging that in. Math 9. To get to cube root, you're going to do math 4. Math 4 will get you that cube root. I should get the same answer. Okay. Any questions? Okay, if you understand this process, if you understand the idea that if you want to do right minus left, you got to rewrite the equations, everything's in terms of y. This is as hard as this unit is going to get. Okay, if you understand this, everything else will just, this is as hard as it gets. This is where students struggle. Okay. Students are pretty good with top minus bottom, but right minus left, the tendency is, you know, it takes some effort to rewrite these equations, and the tendency is students just want to use these equations. But anytime you see anything horizontal, your equations need to be written in different forms. So if you can do this and then understand that your bounds are all in terms of y, then really we're just repeating the same process across, you know, different formulas. All right, any questions? All right, let's do part B. We'll do a top minus bottom and right minus left, and then we'll be done, okay? So let's look at region R now. All right, we want to do top minus bottom, so we're going to be imagining that we're stacking these vertical rectangles from the left boundary to the right boundary. But for region R, though, if I were to imagine all these rectangles being built, are these rectangles going to hit the same graph throughout the entirety of my shaded region? Or is it hitting multiple graphs? So hopefully you guys see that there is multiple graphs involved, especially for the top graph, because for this rectangle here, right, up until a certain point, it is involving that tangent of x. But then after the intersection, a rectangle is no longer going to be involving that red graph. It's going to be involving that 2 minus x cubed. So we do need to split this up into two separate problems if we want to do top minus bottom. But again, top minus bottom is still going to feel easier because you can rely on the original equations. There's no need to rewrite into a different form. Right. We're still going to involve our intersection. So I'm going to write that intersection again. So we'll go from 0 until 0.902. That will take care of this region here. And then from 0.902 to wherever this x-intercept is, will be the second region. So if I want to find this x-intercept, I can just replace y with 0 and solve for x, right? This is the x-intercept of 2 minus x cubed. You can use your calculator to find that x-intercept, or you can find it algebraically. So I'm going to just do it algebraically here. I solved it to be x equals cube root of 2, and cube root of 2 is around like 1.259. But you could also just as easily go into your calculator and do second trace 0, and then find that x-intercept. You can do that as well. Okay, but we need two separate intervals, right? We have two separate top functions, and so we can't just rely on one area formula. Okay, so I'll go from left to right. I'll do the region under the red graph. So from 0 to 0.902. Top minus bottom. So the top is tangent of x. And what's the bottom? What's the bottom equation here? What is this? What's the equation of the x-axis? Y equals 0. And if you look at this equation, this is a good fit for top minus bottom, right? Anytime you see y equals, you know that the right side is a good match for a top minus bottom. Versus if you see x equals, you know that this is an indication that these are good forms for a right minus left relationship. Right, so y equals 0. So that's right. Top is tangent, bottom is 0. Okay, dx. Let's close that off and then work on the second region. So we're going to pick up where we left off from the intersection, which is 0.902, to the x-intercept that we found, so 1.259. Again, top minus bottom. The top of my shaded region is the graph in green, this 2 minus x cubed. Minus, again, the bottom is sitting at the x-axis, minus 0 dx. Okay, so in our calculator, we can just drop the zeros. If you want to go up, go and call the y1 and y2, you can. But see what we get. All right, any questions? All right, last one here. Region R. We're going to do right minus left, so horizontal rectangle. Now imagine this rectangle sliding up and down. Is there a need for 2 integrals, or can we get away with just 1? Is there going to be a change in the right curve or left curve along this path? No change, right? So there's no swap. This region, no matter where my rectangle is, it's always going to be hitting that 2 minus x cubed on the right, and it's always hitting that tangent of x on the left. So even though this is right minus left, this one doesn't need 2 separate integrals. All we need is one relationship here. It's not a split like this one. However, we still have to rely on equations in a different form, but we can just drag that down from R2, right? We can reuse a lot of information here since we did all the work above. So let's rewrite these equations. All right, this should feel easier because since we've done all the work with the previous problem. And we should get the same answer as 0.729, right? Same region, just different orientation. Okay, area equals. We're looking at y values. We're looking from the lowest to the highest y value. Again, y values, right? So the lowest y value is what? 0, the x-axis. And what's the highest y value of my shaded region? Yeah, 1.266. And then we do right minus left. We find the graph on the right of the shaded region, which is the cube root of 2 minus y, and then minus the region, the boundary on the left, which is the inverse tangent of y. Again, you're going to enter this in as x's. Don't use a different variable. Just use x. We should get the same answer. All right, any questions? Okay, so I'm going to end class now, but I want to kind of give you an idea of what's coming up in the next few weeks. So I'm going to go to the calendar here and just show a couple of adjustments we're going to make. Okay, first, there's no homework. We'll pick up on Wednesday. So no school Monday and Tuesday. Wednesday, we'll begin talking about volume by this method. No school Thursday, and then we'll practice more with this method. Maybe we'll start washer method as well. These are the big two topics remaining. And I also want to talk about cross-section. So we should be able to get done. We only have really 3 lessons left. Just this method, washer method, and cross-section. These are all variations of volume. And I need to get in a quiz grade before the 14th, but it's a little too soon. I don't want to do this area volume quiz. I want to have more time for this. I'm going to push this out to sometime, maybe Tuesday or Wednesday. So I'm going to push this out. But I think it's a good, so I don't know what date this is yet. We'll see when this is. But I do need to get a quiz here. But I think maybe it's a good time for us to kind of revisit all of the derivative and integral rules. So we're going to have a quiz on the 12th, just over all the derivative and integral rules. But I will give you a sheet of everything that you need to know, and I'll probably give it to you maybe next Friday, and then you'll have the weekend and Monday, Tuesday to look over it and practice. And then I think there is a total of like maybe 45 formulas. But on the quiz, I'm only going to put like 20 of them on there. But I'll give you a blank sheet of all the 45 things that I could ask for, and I'll attach it to your quiz, and then your quiz will just be 20 of them. So you can fill out the whole thing and then just do the ones that I'm asking for you on the quiz. I have to give you something that I can grade quickly and be able to turn around and then put in the grade book by the 14th. So I'll give this to you next Friday. But this, and I think it's also a good thing for us to do since, we finished basically all of the integral derivative rules. Let's have all that in our back pocket before we do all of our AP exam review. So that's what's coming up. We'll have a quiz, not next week, but the following week, Wednesday. And then I'm pushing out the area volume quiz to maybe next Tuesday or Wednesday, 18th or 19th. All right, come get your phones.
For this phone, does retest work for this one?
No, sorry, this is a strange one.
Okay.
This one, don't worry about it.
This kind of question.
I know, no. Yeah.
Okay, because I saw that you did
I know.
enter on it. I was like, how do you?
And
I saw E. I was like, wow.
nth term. Oh yeah, nth term. If you push n out to infinity, that doesn't equal to 0. Right, so nth term will be a quick one.
Well, I understand that.
Yes.
But-
Like, you're asking why not root test?
Yeah.
So I think the general big picture is always start with nth term
Okay.
and get that out of the way first. And then that way, you can, okay, all right, I've done the easy test. Now let's look at something more complex.
Is it safe to start every single test with one?
Unless it's obvious. It's like geometric theory.
Unless like
So if something is like, it's like, it could be root test. Like, why not just get the nth term out of the way, right? This is so fast, take like 5 seconds to do it. Let's get it out of the way. Even if it returns you inconclusive, it's like, it doesn't take a whole lot of time. And root test is like, oh my gosh, I'm like stuck. Like, what do I do? It's hard to go back to think, wait, oh, maybe I should have done nth term at the beginning. Yeah, but I won't give you that one. That gives you a
Yeah, it does.
But the lesson learned is nth term.
Oh, I just have a question. Was this homework assigned on Monday?
No homework.
Oh, okay.
Yeah, no homework.
Okay.
No.
So it's the, I don't know, yeah. I should be sitting on my camera. And I'm listening to it. Yeah. I just got here to be out. Yeah. I think so. No, I didn't have to get up and.
You haven't taken, oh, you started already?
Yeah.
You can finish, okay. Copies.
You actually.
Oh, this one.
You just think about it. One over initial revenge. Could you just look at that as like something like a lesson?
I think I did direct comparisons. No, wait, no, sorry, this is alternate series test. Yeah. Because the limit of that 1 over n does go to 0. So that's good enough for alternate series.
Because I got that these two conditions happen,
Yes,
but it said on the kit that it's conditionally convergent, which means
that means.
why does this type?
Okay.
That.
That's. Yeah.
Oh, this is.
Direct events.
Oh, yeah.
I did direct.
Also, I can't compare with 1 over n. Because that's what I was thinking in my head. I didn't think it was-
Because this is smaller than this, which must have been. Like,
It's okay, because I do have to write that out, or, because I made the connection in my head, I just didn't think it was easy. Can you give me a sense, like, if it doesn't take too much time, you can say, well, what, the questions that I test my.
The what?
What, like a question that test my. If it doesn't take too much time.
Let me see. I have. Review, I thought I put something on the back. There you go. Okay, yeah. The test review here.
Yeah, I don't know why it says.
Cover these up and just see if you can decide what you're gonna do for each of them.
That one's GST. Serious. That one's just.
Wait, this is integral test.
Yeah, sorry. That's my. My head. This is AST. This one. Or the comparison.
Limit comparison.
Okay. So just limit comparison.
That's what I would do, limit comparison.
Okay. Can you
Easy.
potentially use?
Use what?
Can you potentially use?
Direct comparison?
Yes.
You could, but
this-
it's so much easier with limit comparison.
This is ratio test, root test, and then I guess this is DCT.
Yeah, DCT is like, especially if you're new